Hello and welcome. This is going to be our lecture for the Angular Kinematics worksheet. We'll go ahead and get started on the second page of this because I feel like we did the first page pretty well in class. All right, so let's go over problem number 4. We're going to need a few formulas here. One is that angular velocity is equal to the angle that you turn divided by the time that it takes to turn that angle. And then linear velocity is equal to your angular velocity times your radius. These two formulas are going to be able to help us answer pretty much all of these questions. We should also remember that 2 pi radians is equal to 1 revolution, and pi radians is equal to 180 degrees. From those conversion ratios, we should be able to do all of our angles. All right, so a computer hard drive spins at 7,200 RPM. So first thing I'm going to do with that 7,200 is split it up into revs per minute. And I'm going to write it like this in a fraction line. All right, now I need to convert this to rads per second. So I need to get the revs, which is on top, to be rads. One way to do that is to put 1 rev is equal to 2 pi rad on the top. And then it's rads per second. So right now I would have minutes on the bottom. To get seconds to be on the bottom, I'll use the conversion factor that 1 minute is equal to 60 seconds. And now minutes will cancel, seconds will be my new unit on the bottom, rads will be my new unit on the top. I multiply straight across the top and straight across the bottom and divide. And that's how I get 754 rads per second. Now, what is the velocity in meters per second of the hard drive? So here we need the velocity formula at a radius of 0.0889. So velocity equals our angular velocity. It has to be in rads per second. So 754 times our radius, just straight from the problem. And that's how we get a velocity of 67 meters per second. All right, moving on. Number 5 is pretty similar. Convert that revolutions per minute to rads per second, and then multiply that by the radius. Let's go over all the questions for number 6 here. How many revolutions does our merry-go-round make in 3 minutes? So we're using a version of distance equals speed times time. So total revolutions will be revolutions per minute times number of minutes. So if I'm going 15 revs per minute, and I multiply that by 3 minutes, the minutes will cancel out, and I'll be left with 45 revs, which is what we see over here. All right, how many revolutions will it make in 10 seconds? So I can do something similar, 15 revs per minute times 10 seconds, but here seconds don't cancel out minutes. So I will throw into the conversion the fact that 1 minute is equal to 60 seconds. Now seconds will cancel, minutes will cancel, and I'll be left with just revs. And we can see we get 2.5 at the end of this. 15 times 10 is 150, divided by 60 is 2.5 revs in 10 seconds. How long does it take for a person to make 1 complete revolution? So here we just simplify the fact that if it's 15 revs per 1 minute, well, we don't really simplify it. We just flip this upside down. We just say, well, then in 1 minute, we'll make 15 revs, and then we simplify this fraction. 1 divided by 15 is some decimal times 60 seconds in 1 minute is where that 4 seconds comes from. All right, and the last one, what is the velocity in meters per second of a person standing on the edge? So we need to convert the speed from RPM to rads per second. So 15 revs over 1 minute, we'll multiply that by 2 pi over 60. It's kind of our shortcut for converting to rads per second. And then take that result and multiply it by the radius of 1.75, and we should get 2.74 meters per second. All right, let's move on. All right, how about problem 10 here? Let's talk a little bit about the angular velocity of the hour hand, minute hand, and second hand of a clock. So for the hour hand, we know how quickly it rotates, but we don't know it in rads per second. We know that the hour hand rotates at 1 revolution every 12 hours. All right, we even have a clock down here to look at, and it goes around once between midnight and noon, and then again between noon and midnight again. Now we just have to convert this to rads per second. So to turn revs to rads, you go 1 rev is equal to 2 pi rads. And then to convert hours to seconds, we just use the fact that 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. Multiply across the top, multiply across the bottom, and divide. Just make sure our units cancel appropriately. We get rads per second, good. And we should get 1.4 times 10 to the negative 4th rads per second. And to get RPM, we would just, we could do something very similar, but instead of converting to rads and to seconds, we'll just do only the conversion of hours to minutes. So 1 rev every 12 hours, just multiply it by 1 hour is equal to 60 minutes. Hours will cancel, and then just remember to divide in that last step. 1 times 1 is 1, 12 times 60, whatever that is, 1 divided by that, and we should get 0.0014 revolutions per minute. All right, moving on. For number 11, you just multiply these radiuses by the angular velocity, but you have to do the rads per second times each of those to get the appropriate velocities. All right, rads per second is designed so that we don't have to do any other conversions to quickly do anything with distance or speed around the circumference. All right, a wheel is spinning at 5 rads per second. How many radians will it turn through in 20 seconds? So we're just start with what we're given, 5 rads per second. It turns for 20 seconds, so we'll multiply by the 20 seconds. Distance equals speed times time. And seconds cancel out, and we'll just be left with radians. So that's how we get 100 radians. So 100 rad, that matches our answers. How many revolutions is this? Now we'll take our answer and we'll multiply it by the fact that 2 pi rad is equal to 1 revolution. And then you multiply it across the top. 100 times 1 is just 100. Divide by the 2 pi, and you'll get approximately 16 revolutions. Won't be exact because 2 pi is irrational. Okay. All right, how long will it take a helicopter blade to turn through 200 radians if its angular velocity is 60 rads per second? So we'll start with that rate, 60 rads per second, and let's flip it upside down. We can say if it's going 60 rads per second, every 1 second we go through 60 rads. And then we can multiply by the 200 radians to get a unit of seconds on top. And then 200 divided by 60 gives us our 3.3 seconds. Okay, a baton twirler spins a baton at 25 RPM. What's the angular velocity? So 25 revs per minute times, and then we do this one so often that you can use the shortcut, just multiply by 2 pi over 60, and you're going to get 2.6 rads per second. How many rad will it travel in 4 seconds? So if it's going 2.6 rads per second times 4 seconds, seconds cancel out, and we're left with just radians on top, and we get 10.5 radians. All right, which is greater, 45 RPM or 4.71 rads per second. We want to get them to be the same unit, so we can just use that 45 times 2 pi over 60 trick yet again, and you'll see that you get about 4.71. So they are the same. If you go out to the third decimal place, the 45 RPMs wins slightly because it's got 3 or something right here. So it says that they're the same. Technically, the 45 RPM would slowly outpace the 4.71 rads per second. All right, 17. What is the angular velocity of the smaller wheel if the angular velocity of the larger wheel is 6.5 radians per second? Hint, they'll have the same linear velocity. So that kind of tells us we should find the linear velocity. So v equals our angular velocity times our radius. So here the velocity is equal to 6.5 times 0.35. And we get a velocity of 2.275 meters per second. So that's going to be the same for our smaller wheel too. So the velocity is going to be 2.275 meters per second. Its angular velocity will be different though, and its radius is 0.12. So divide both sides by 0.12, and we get 18.95 rads per second, which is about 19 rads per second. All right. Acceleration works the same way with angular velocity as with normal velocity. It's change in velocity over time. So if we went from 0 or from 5 to 0 in 30 seconds, it would be a change of -5 divided by the 30 seconds gives us -0.17, and then the units are rads per second squared. All right. Another angular acceleration one. Just treat this acceleration. Well, okay, we can do A real quick. Starts from rest, our initial angular velocity is 0. And then we accelerate at 0.75 rads per second squared. All right, so if we multiply this by 60 seconds, only one of our seconds will cancel and we will get a final unit of rads per second. And this here is going to give us that 45 rads per second. How many radians have they rotated through? You need kind of a more sophisticated kinematic for that one. Why don't you just skip that one? And then the linear velocity of the tip of the rotors at the very end, we can just multiply the rads per second times that 7.3, and we should get 329 meters per second once they're up to speed. All right, we'll call that good for this lecture video. Have a great